Okay. Let us take another problem. Find dy by dx where y is given as 0 to root x cos t dt. And there are two problems, one more is 0 to sin x. Similarly, we will come back to that. First, let us see the part A. So, y is given as 0 to root x cosine t dt. Our fundamental theorem says that 0 to or a any a to x f of t dt. If you take this as function y, then dy by dx, so that is y prime, will be equal to its prime, that will be equal to f of x, right, provided this function is continuous and so on. So, now what do? We straightforward go for derivative, that will be equal to f of x if it is in the form a to x, but it is not in the form a to x, it is 0 to root x. A, of course, we can take that constant to be 0. Problem is dy by dx we want, but it is 0 to root x. If you take dy by d root x, then straightforward we will go for cos root x, right. So, you used to put chain rule, right, apply chain rule here. Now, dy by dx is dy by d root x into d root x by dx. So, d root x by dx is 1 by 2 root x, and d root x of 0 to root x is it is really something like u, d by du 0 to u. So, that gives you cosine u or cosine root x. Therefore, the answer is cosine root x by 2 root x. Now, similarly, we will try b. In b, instead of root x we have sin x. So, y equal to this. Of course, we can do easier way here, because we find that 1 by 1 minus t square is the derivative of square root of 1 by square root of 1 minus t square is really derivative of sin inverse t, right. So, we can do better way, we keep 0 to sin x as earlier instead of applying straightforward the earlier technique in A, and we can integrate it. So, 1 by square root of 1 minus t square gives sin inverse t evaluated at sin x and 0. At sin x it gives x, sin inverse of sin x. So, remember our inverse functions, this notation only is giving the principal value. So, we have nothing else. If you do not get the principal value, we have to add some multiples of y. So, it is sin inverse of sin x, since it is principal we get x back, and at 0 it is sin inverse of 0, that also is 0. So, now you see, if you had you taken some other principal instead of the principal part of sin inverse, if you take other parts, there can be a difference of multiples of pi, right. Anyway, our notation is only for the principal. So, that is sin inverse t is that number whose sin is equal to this and which really remains inside the interval 0 to pi by 2, right, or 0 to pi, one of them, or minus pi by 2 to pi by 2 or 0 to pi. That was our definition. Okay. So, what we get is y is equal to x, therefore, dy by dx equal to 1. You can do otherwise also, but that will be slightly complicated here, because you have to write d of dx of sin x, and then this will be 1 divided by square root of 1 minus sin square x, that gives you 1 by cos x, and that cos x will be there, that will be cancelling, that will also give you 1. Okay. So, if you want to see how it goes, you may write it is d sin x by dx times derivative of this with respect to sin x. So, that will give you f of sin x, that is 1 divided by square root 1 minus sin square x. So, now this gives you, first one gives cos x, this gives 1 by cos x, and also you get 1, right, using the technique used in A. Fine. So, let us go to sixth problem. We want to find the total area of the regions bounded by the curve y equal to x to the power 1 by 3 minus x. the x axis, the lines x equal to -1 and x equal to 8. So, it is written regions, there might be multiple regions, right. Total area we want to find, but there can be multiple regions or maybe only one region, we do not know. But then it will be something this way, not exactly we are plotting. So, conceptually, so there can be many points where it will cross the x axis, then you have to find out these areas and add them up. That is what is being asked. So, let us find first where does it cross the x axis. Okay. So, where does it cross? X to the power -1/3 minus x must be equal to 0. When you take this curve, it crosses x axis, that means y equal to this function. So, this must be equal to 0 and that is 0 for x to the power 1/3 equal to 0 or x to the power 2/3 equal to 1, right. If you consider x to the power 1/3 into 1 minus x to the power 2/3 in this form. So, either x to the power 1/3 is 0 or x to the power 2/3 equal to 1. So, that gives you 3 points now, -1, 0 and 1, right. Of course, if you take -1 here, that gives you -1 to the power 1/3 and this is -1. So, -1 plus 1, that is equal to 0, that also happens. So, there can be 3 such points. So, that means we have to really break it into 2 integrals. One is from -1 to 0, another is from 0 to 1. So, let us consider those intervals. -1 to 0, in that interval, what about the function? That remains negative, right, less than or equal to 0, because x to the power 1/3 will be bigger than x, it is -1 to 0 only. Okay. This is less than or equal to 0 and from 0 to 1, it is really greater than or equal to 0. Okay. And we have the line -1 to 8 we want. So, from 1 to 8 there is another interval. So, 1 to 8 it is again less than or equal to 0. Okay. So, we want to find the total area, nothing is written. So, we take the actual area, not the signed area, sum of all those actual areas. So, the required area we can write as, since it is -1 to 0, it is negative, we should put a minus sign to get the actual area. So, minus of x to the power 1/3 minus x, that becomes now mod of this. So, minus is outside and then 0 to 1 it is greater than or equal to 0. So, mod of that is itself x to the power 1/3 minus x and 1 to 8 is negative. So, it is minus 1 to 8 x to the power 1/3 minus x dx. Now, x to the power 1/3 minus x has the integral, indefinite integral as this, because if you differentiate this, it is becoming x to the power 1/3 and this gives x. So, this is the indefinite integral. As it suggests, we have to take minus of this evaluated at 0 to -1 plus that evaluated at 1 and 0 and minus that evaluated at 1 to 8. Fine. So, we substitute back all these expressions and simplify. So, that would give 83 divided by 4. So, you can verify it later how exactly it comes, but this is the expanded form and then simplification gives 83 by 4. That is our answer. So, we may have to really consider these things. We have not plotted it, because in general sometimes you will not be able to plot the one easily, but still your analysis should be able to point out all the details. Okay. Let us find out what happens in this problem. So, here we want to evaluate a limit as x goes to 0. What is the function? It is 1 by x cubed times an integral. Okay. So, of course, you can integrate this, fine. It is t fourth divided by t square plus 1. You can take t fourth minus 1 by t square plus 1 and plus 1 by t square plus 1. First one gives t square minus 1, and second one kept as it is. Now, its integral, this you can integrate just like a polynomial, this will be tan inverse t. So, you can really integrate, substitute x and then go for the limit, fine, but that will be a bit lengthy. So, what we do? We look at this, what is happening. As x goes to 0, its denominator is x cubed. So, that goes to 0. Now, the limit does not exist if the numerator does not go to 0 when x goes to 0. But what is the numerator? It is integral 0 to x t fourth by t square plus 1 dt. When x goes to 0, this continuous function x goes to 0. So, it will be 0 to 0, integral will become 0, right, that will be the limit. Okay. So, integral becomes 0 when x equal to 0, that is limit of the numerator is 0, limit at the denominator is also 0. So, it is in 0 by 0 form, fine. So, you can use straightforward L'Hopital's rule. So, if you apply L'Hopital's rule, this will be equal to, provided this right side limit exists, equal to limit of the derivative of this function divided by derivative of x cubed. So, derivative of x cubed is 3x square and derivative of integral 0 to x by fundamental theorem is x fourth divided by x square plus 1. That is why we get this limit by L'Hopital. So, it is limit x goes to 0, x fourth divided by x square plus 1 times 3x square. Now, x square cancels. So, it is really x square divided by 3x square plus 3, and that limit is straightforward 0 because numerator goes to 0, denominator goes to 3, fine. So, there can be simpler ways, we have to really find out which one becomes simpler. Sometimes the other method can be simpler, that is evaluate the integral and then do it instead of doing this way directly. Let us see the next problem. So, here we want to determine f of 4 given that integral 1 to x f of t dt equal to x cosine pi x plus 1. We have no idea on f, but only given that integral of f is something. So, here what we do? We can find out really f of x here, right, directly by differentiating this. If you differentiate the left side, we would get f of x, it is the integral 1 to x f of t dt, and you differentiate right side, of course, you get something, right, 1 gives 0, x cosine pi x will give you derivative of x is 1. So, cos pi x and plus x cos pi x derivative is minus sin pi x into pi. So, that will be f of x, then you can substitute 4 and get f of 4, fine. That is what we do. Or if you just integrate, anyway you wanted that integration. So, if you integrate also, the same thing can be done. So, first thing we just explained using the technique is 7. Now, the other way also you can do it, say 1 to x f of t dt, if you try to find out, then what does it give, right. So, that way also you can get directly integrating this x pi x plus 1. But how do you integrate? If it is given f of t, you will not be able to integrate, but you have to really differentiate. So, first find what is the derivative of x cos pi x plus 1. Anyway, that derivative is required, right. So, you see f of x will be equal to this, and then that gives you f of 4 equal to cosine of 4 pi equal to 1. Since f of t is not given, you cannot really integrate to get that expression what it is. You have to go back to fundamental theorem of calculus. So, that is what we have done. We found 1 to x f of t dt equal to x cosine pi x plus 1. If you differentiate, the derivative is giving you f of x. So, f of x is derivative of the right side, and that is it. Okay. Here in the next problem, we want to find the linearization of a function. Okay. So, linearization of a function, you know, at x equal to a would be written as L of x, and that is equal to f of a plus f prime at a into x minus a. That was our linearization. And now in this case, f of x is given in terms of an integral. So, f of x is 2 minus integral 2 to 1 plus x 9 by 1 plus t dt, and we want to find a linearization at x equal to 1. Okay. So, that means we need f at a, we need f prime at a, that is at 1, f at 1, f prime at 1. So, we should get f prime by differentiating this integral by using our fundamental theorem calculus. So, it is pretty straightforward. First thing is f of 1 is 2 minus integral 2 to 1 plus 1, which is 2, 9 divided by 1 plus 2, 1 plus t. So, it is integral 2 to 2, that becomes 0. So, you get 2. Then you take f prime x. Here it is the variable is 1 plus x on the top. So, all that we know, it is a to x f of t dt, its derivative with respect to x is equal to f of x, but here it is not x, but 1 plus x, right. So, we should find derivative of with respect to 1 plus x first. That is not very big thing, it will be same, because derivative of 1 plus x with respect to x by chain rule will give you 1, right, in this case. So, that gives derivative of 2 is 0 with respect to x, and derivative of this integral is derivative with respect to 1 plus x times derivative 1 plus x with respect to x. And with respect to 1 plus x, and when the top limit is 1 plus x, that gives you f of x, that is 9 divided by 1 plus, in place of t it will be 1 plus x, right. So, that is what the answer is, minus 9 by 2 plus x. So, and what is f prime 1 then? So, as you see, f prime of 1 equal to minus 3, from this you get. So, once f prime is obtained at 1, f 1 is obtained, linearization is just a formula, that L x equal to this is plus, right, f of a plus f prime at a into x minus a. So, that gives you, this should be f of 1 plus, what is f prime 1? It is minus 3. So, this expression is correct. It is minus 3 into x minus 1. So, that gives you minus 3x plus 3 plus 2, which is minus 3x plus 5. That is the linearization near x equal to 1. So, let us stop here.